Okay. Can you hear me?
Yes.
Okay. Good.
Hi, Kimitoshi, by the way.
Hi.
Got all the speakers and a chair on stage. And yeah, I think attendees are slowly coming in. So I'll keep myself muted, but I'll keep my camera on. And I will request a confirmation from Uday when the link is alive.
Just to say, Kimitoshi, my plan is to keep the introduction very short. So I will just say, we have a very exciting session with 3 great speakers, and the first speaker is Kimitoshi Kono. And then in your first slide, you will give the title of your talk and your affiliation. So I think it's most efficient to do that. And I'm not going to pretend to summarize what your talk is going to be about before you actually give it, because I don't know. I might guess, but I don't want to guess wrong. So and there's really no point in that. So that's my plan. So the brevity is not intended to convey a lack of respect or anything like that. Obviously, obviously not. I mean, but there's no point in me spending 5 minutes about saying what a great guy you are, because there's no. You've already said that on your biography on the site. So. Yeah. There's some very strange squeaking sounds going on now.
I think we should keep our mics muted, otherwise there's a lot of feedback that comes.
Okay.
I wanted to let you all know that right now we are live on YouTube, and we're also keeping an eye on who all are joining this event through YouTube. It's about to be 5:30. We'll just start about a minute after that. All right. Welcome, everybody. My name is Ambarish Ghosh, and I'm one of the organizers of the Quantum Fluids and Solids International Conference, also known as QFS 2021. Today is a special event. We are going to have a plenary session which will be not only attended by all the registered participants in this hall, but also broadcasted live on YouTube. I'm requesting Professor John Saunders to chair this session, and before I hand him over the screen, let me read out his biography in just a few minutes. So Professor John Saunders is at the Royal Holloway University of London, and he is the director of the London Low Temperature Laboratory, which is also a part of the European Microkelvin platform. He obtained his PhD at the University of Sussex, followed by a postdoc at Cornell. His current research is on quantum materials and quantum technology at ultra-low temperatures, including thin helium films, topological superfluid helium-3 under nanofluidic confinement, strongly correlated electron systems, and quantum devices. This research features development of new techniques and instrumentation, NMR with superconducting devices, noise thermometry, cryogen-free ultra-low temperature platforms, and nanoelectromechanical resonators. So with that, I would request John to take over and chair this session. Thank you, John.
So thanks very much for that introduction, Ambarish. And it is indeed an honor to chair this afternoon's session. Well, it's the afternoon in the United Kingdom at any rate. And we have a lineup of 3 highly distinguished speakers discussing a range of pertinent topics, all of which have a very interesting history and also, I believe, a very exciting future. Our first speaker, I'll introduce without further ado, is Professor Kimitoshi Kono, and I'll hand over to him straight away, and he will describe his affiliation and the title of his talk. Thank you very much.
Thank you very much, Mr. Chairman John. So now I try to share my screen. Okay, I think it works now. Okay. And first of all, I would like to thank Ambarish Ghosh organizing such nice online conference under such hard time. And today, I would like to talk about extrinsic particle states to uncover intrinsic quasi-particles in superfluid helium. And so extrinsic means, so when we talk about superfluid universe, the main ingredients is quasi-particles or order parameter collective mode or such intrinsically related to superfluid vacuum. But today I will talk about a little bit different kind of void formed in vacuum or superfluid helium. And I think there is no such object in our own real universe. Okay, so now before starting my talk, I would like to thank many people. In particular, first collaborators, Hiroki Kegami from Riken and Sukubun Chun in Seoul University, and Tsutsumi-san now in Kansei Gakuin University, and Peter Moroshkin and Paul Lydra and many others. And in particular about superfluid helium, it is inevitable for me to have theoretical inputs from many distinguished theorists listed here. Okay. And so I will first talk about what are extrinsic particles in superfluid helium. Okay. And then just example of what is extrinsic particles. And then main subject today is electron bubble and snowball. And first, I would like briefly summarize the history of this object, electron bubble and snowball in helium-4, and then continue to superfluid helium-3. And then if I have some time, I just want to mention about metallic clusters. Okay. And so there are quite many systems known as extrinsic particle or extrinsic impurity. And so first, electron is known to form electron bubble. I will explain later a little bit more detail. And not only single electron bubble, but also there are multi-electron bubble. And recently, chairman of this QFS, Ambarish Ghosh group, made quite fascinating observation, and it was already reported on the few days in this conference. And surface state electrons, I studied quite a long time for this subject. And at some time I started to make experiment using helium ions, negative, so bubble and snowball. Okay, and so these two are quite famous or popular to quantum freeze and solid people. And also alkaline and alkali earth atoms also known to form bubble state. And molecules are also studied. And I think for these species, helium droplet or cluster is, I think, main place to work. And XMI is a molecule formed with excited state of either helium or metallic atoms or a combination of ion and helium atom. And then a cluster of such alkali metal or hydrogen is also very popular, in particular in the study of turbulence and quantized vortices in superfluid. And then ions also make a exotic state, and either a positive or negative ions. And most ions form a snowball, but barium is known to form bubble state. So today I will talk about electron bubble and a little bit about snowball. And also we studied dispersion, this atomic bubble and XMR and barium cluster and these ions. But unfortunately, I may not have enough time to talk all of them. And this review article is, I think, quite nicely introduced most of these exotic species. And first, electron bubble and snowball. The electron bubble is...
Kimitoshi, can I quickly interrupt you and remind you, please, could you turn off your video camera? It helps with the YouTube presentation. Thank you.
Okay, yeah, thank you. Thank you very much. And electron bubble and snowball. Electron bubble is an electron trapped in a cavity void of helium atoms, like this. And this structure was proposed by Ferrer to explain the long lifetime of also positronium. Positronium is a pair of electron and positron, like a hydrogen. And so electron act Pauli exclusion repulsive force to helium atom and to form a void structure. And inside this void, positronium lives long. And the snowball is a cluster of helium atoms attached to a positive ion, helium plus, or maybe helium 2 or helium 3 plus is more recent understanding of the core structure of ion. And electrorestriction or polarization of helium atom due to central charge make polarize helium atom and then attract helium atoms around positive charge. This is a basic structure of snowball. And then, okay, so the size, to find the size and structure of ions, the following consideration is usually employed. The bubble formation results in a reduction in the kinetic energy of electron. So compared to very narrow space inside liquid helium, after forming bubble, the 0-point energy reduces. And it costs surface tension energy and electrostatic energy this time, and also work done against pressure. And to minimize this energy, for example, at zero pressure, at a very low temperature with free surface, and this term is negligible usually. And so it will give 1.9 nanometer for helium 4 and 2.4 nanometer for helium 3. And for snowball, due to the electrorestriction, the pressure at R from the helium plus core is expressed by this quantity. Alpha is polarizability of helium atom, and N is density of liquid helium. And epsilon is a dielectric constant. So the electric constant depends on the density of helium atom. And so estimate can be 0.6 nanometer, much smaller than bubble. Okay. And then the experimental determination of the size is done by Tito Williams group in Sacre. And so they employed the ion trap at the free surface. And it may be the first demonstration of accumulating ions just underneath the free surface. Any charge approaching to the free surface feel repulsive force due to image charge located outside the medium. And then applying external electric field, uniform electric field to press ion towards surface, we can produce potential minimum to trap ion. And so this is for positive ions. And then so forming some resonance circuit and at fixed resonance frequency, tuning the electric field slope of this field, and then curvature of this potential minimum changes. And for negative bias, so this is negative from the bottom electrode, electron signal appears. But for positive biasing, the snowball appears resonance here. And by analyzing the resonance frequency, knowing this curvature or natural frequency, the positive ion effective mass is 43, and radius is 0.6, and the electron bubble is 243 helium mass, and size is 1.7 nanometer for helium 4. And it is quite coincide with previous estimation. Okay, and then ion transport is one of early experimental technique, and it revealed quite unexpected behavior. And most of you already know this famous experiment by Layfield and Life, trying to measure the drift velocity of ions. And they prepare some acceleration area where electric field is finite, and then inject this accelerated ion into free space to travel. And by changing the electric field strength, the energy provided to ion can be changed. And by increasing input energy, the velocity drops almost inversely proportional to energy. And so it is understood by trapped ion by vortex ring. And so supplied energy is spent to expand the diameter of this vortex ring, and speed of vortex ring is inversely proportional to the diameter of the vortex ring. And so the reason why larger energy ion have slower speed is attached to vortex ring. And this is quite amazing observation. And then from linear transport regime to vortex ring associated composite state is sharply show some transition behavior. So at certain acceleration speed, and then it dropped to show this vortex composite, vortex ion composite. And okay, and then it is interesting observation. And in linear regime, the mobility can be measured very precisely. So by this group in Birmingham by Professor Joe Bynent group made this temperature dependence of bubble mobility. And this mobility, temperature dependence, is quite good show agreement with the theory by Bain and Barrera-Pesce. And so the mobility of electron bubble is determined by scattering of phonon in liquid helium at low temperature. And the theory is considering electron bubble as an elastic material and sound same as classical sound wave scattering by this elastic object. And then the total cross section shows some peak structure as a function of wavelengths or wave number. And first peak is S wave, and this is corresponding to just a breathing mode of bubble. The bubble radius is expand and shrink and oscillate. And then, so P wave is a kind of shaking mode. And then D wave is quadrupole oscillation of electron bubble. So this is a basic mechanism of scattering in superfluid helium form. And then about snowball, the Gary Williams group in Los Angeles, UCLA, measured cyclotron, plasmon resonance of ion pool accumulated on the free surface, and they found linear temperature dependence of effective mass of snowball. And this temperature dependence was quite puzzling, but for now, so far, I think Elza and Platzman developed theory to interpret this dependence, and their claim is some anisotropic structure introduce such linear temperature dependence. Okay, and for now I go to helium-3, and this is a phase diagram of superfluid helium-3 taken by the famous textbook written by Grisha Volvic. And so this is temperature and magnetic field and pressure. And at least A phase and B phase is well known or established. And B phase occupy this region, lower temperature and smaller magnetic field corner. And in particular, high magnetic field and also high pressure region, the A phase predominate over B phase. And so this plane is solidification, and about this pressure, system becomes solid and no superfluidity. Okay. So, and then just brief reminding some brief property of how is helium-3A and helium-3B. And so this Cooper pair of helium-3 atom forms eigenstate is corresponding angular momentum equal to 1, and orbital angular momentum is 1, and spin angular momentum is also 1. And it forms P wave or triplet superfluid. And A phase is corresponding to the eigenstate of Cooper pair corresponding to Lz equal to 1. So projection of orbital angular momentum is equal to 1. And spin angular momentum projection is 0. And then the A phase has a point node in energy gap, and it has chirality because Lz equal to 1. So along some quantization axis, the motion is just circulating in one direction. And also finite Lz means time reversal symmetry is broken. And as for B phase, so J equal to 0 is eigenstate of Cooper pair, and J is total angular momentum. And so J equals 0 means a system is quite isotropic, and the energy gap is isotropic. So just schematically, A phase has node in energy gap, and if there is some surface, or free surface of liquid helium, this direction, node direction is preferentially oriented to perpendicular to the surface. And this arrow is showing this anisotropy vector, and it is called L vector in this A phase physics. And B phase is isotropic energy gap. But approaching to surface, the order parameter changes. Okay. And in bulk system, superfluid helium-3, bubble mobility and snowball mobility is measured quite early days of helium-3 study. And so mobility of negative ion shown here is obtained by Helsinki group, and theoretically, and A phase and B phase show different value in mobility. Mobility normalized at normal fluid value. Okay, and then later this Roach, Ketterson, and Roach measured this mobility in A phase. And the A phase show anisotropic behavior. So for this experiment, magnetic field is used to align L vector. L vector align parallel to the magnetic field, right? Not perpendicular to the magnetic field. Okay. And then this is order parameter near to the surface, specular surface. And for A phase, the energy gap orient perpendicular to the surface. Surface is located this Z equal to 0. And no change into bulk. And so for A phase, having this orientation of L vector, specular surface does nothing. And but for B phase, the energy gap or order parameter distort approaching to free specular surface, and perpendicular component perpendicular to surface is reduced. And parallel component in this direction is slightly enhanced. Okay, so this is taken from this paper by Nagai et al. And Z here is coherence length of superfluid helium, and it is h bar Vf Fermi velocity divided by pi kbTc. So this is the order of delta. So for helium B phase case, we can use delta instead of this quantity. But for A phase case, it is not clear which delta is should be used. But maybe Tc is uniquely defined. And again, at the surface, image charge repulsion and externally applied electric field produce minimum in the range of 30 to 60, 70 nanometer from free surface. And this position is quite comparable to order coherence length. And in this range, order parameter, in particular B phase, should change quite a lot. And okay, and then so we studied these ions and bubbles trapped just under the free surface of superfluid helium 3. And the first report was done in 2002, but quite final data is obtained by Ikegami and published in 2013. It took a rather long time to get final result. Okay, but I will come on this data later. So this is for B phase. And so starting from A phase now, and so in A phase, Reiner and Gorio reported the possible current circulating about bubble, electron bubble, indicated by this red circle. And so the theory is based on Ginzburg-Landau regime, and so it is a kind of rather long-range distortion of order parameter or texture. And later, the Salmenin, Salomar, and Minev wrote paper about some anomalous Hall effect. So in recent time, and in one of the figure in this paper showing some close-up near the nodal point in A phase. And then, so at A phase, this is energy gap as a function of, say, momentum in X and Y directions. So supposing this perpendicular direction is Z direction. And then inside energy gap, there should be some bound state should appear. But in the presence of continuum here, and some mixing should occur and give some lifetime and also some broadness to this bound state, and it becomes a quasi-bound state. And so this paper also state, scattered quasi-particle interferes with the tendency to form Cooper pairs, bringing about bound states within the delta. So this is saying this thing, and a strongly energy-dependent cross-section, and etc. So it is some general expectation from theorists. Okay, and so we or Ikami-san measured this anomalous Hall effect. So this quantity alpha is ratio between sigma xy and sigma xx. And so without a Hall effect, so this sigma xy should be 0. And using free surface, we can align L vector perpendicular to the surface, and also current direction is parallel to the surface. And so the L vector and current is perfectly perpendicular. And so to form or realize this geometry is only possible using free surface. So in principle, it can be, this experiment can be done in bulk, but in practice, only free surface is the appropriate playground. And so these two dots are data from our paper. And Shevtsov and Soros really developed theory to explain this observation, and agreement is surprisingly good. And this theory by Shevtsov and Soros says, so for example, the current calculated, so this is supposing bubble, this gray sphere is bubble, electron bubble. And then about this position, some current is circulating in this direction, clockwise direction, and supposing L vector is upward in this direction. So the angular momentum of this current is opposite to this L vector. So because void is effectively cancel this background field, bringing opposite angular momentum inside this bubble. And in addition, the polar plot of differential cross-section shows this spiky structure, and so quasi-particle is coming from this direction and scattered in this direction in the same plane. And then there are such structures, and so big enhancement in forward scattering and reduction in backward scattering. So this is the reason why the mobility in superfluid phase increases compared to normal phase. Okay, and then so important statement is also found in this paper. The observation of the anomalous Hall effect for negative ions is not only a signature of broken time reversal and parity symmetry, but a signature of chiral fermion circulating the electron bubble. So it is saying this current induced around bubble is due to chiral fermions or wild fermion. Okay, and then they also calculated local density of state about the position with respect to bubble. And the energy gap is orienting in this direction. And then inside energy gap, for maximum energy gap, there is some tail due to nodal point in superfluid A phase, also in bulk. But so approaching to this bubble from bulk inside, and then this spiky structure is showing, and this is indication of bound state or quasi-bound state around this electron bubble. Okay, and then this density of state is resolved by this projection of angular momentum, and then it shows from positive projection to negative projection, the bound state, quasi-bound state energy shows this behavior. And so only one branch appears, and it is chiral or wide fermion characteristic. Okay, so it is quite clear to show such quasi-bound state around the bubble. And another important observation is this anomalous Hall effect signal only found in A phase, and no such signal in B phase. So this is implying the free surface of the B phase is not A phase. So for thin slab of helium B should have transition to A phase, but surface is not certainly such case. Okay, and then before going to B phase, just remind a little bit about scattering theory or scattering problem. And asymptotic wave function of incident and scattered particle from a centrally symmetric potential must be written like this. So this is incoming wave, plane wave, and this is outgoing scattered wave. And the coefficient F is called scattering amplitude, and this is characterize the nature of scattering. And scattering cross section, the sigma is then using the scattering amplitude given by this quantity. So the omega is an element of solid angle. And so total cross section and transport cross section, sigma total and sigma transport, given by this integration. So differential cross section integrated by solid angle should give total cross section, and transport cross section is just weight of this 1 minus cosine theta to differential cross section. And so so for this quantity, so theta equals 0 is forward scattering, and cosine equal 1. And so no weight for this scattering, forward scattering. Maybe it is of course maximum. And then backward scattering is most important for transport cross section. And also just simple scattering scheme is scattering due to some quasi-bound state, like this potential profile. And if this area has some quasi-bound state, and then scattering should show quite strong energy dependence by sweeping energy. And energy coincide with these levels, the scattering is very much enhanced. But when the bound state is a real bound state, and then but still scattering should occur, quantum mechanics, and then this existence of this bound state also have contribution to this scattering. Okay, and so this case may be corresponding to A phase case, because A phase has nodal point, and we have quasi-particle flying in liquid helium, superfluid helium. But for B phase, energy gap is isotropic, and so even if there is some bound state inside below delta, there is no such quasi-particle which can probe these states. Okay, so there is no directness. So in the vicinity of surface, now come to free surface again, and there is no the Andreev surface bound state or quasi-particles exist, and these surface state, bound state, have access to this bound state, because Andreev bound state can enter below delta. Okay, and so first mobility in bulk. This is experimental point, And if the scattering cross-section is assumed to be same as normal phase case, and then only the reduction of thermally activated quasi-particle reduction due to energy gap is origin of reduction of mobility. But real experiment is so inverse mobility. And so mobility further increase with respect to this line. And this is due to the change in scattering cross-section due to superfluidity. And it is calculated by Bain, Pesek, and Saloma. And the solid line here is from this paper, or this figure is from this paper. And then later in this paper, they showed this diagram, differential cross-section as a function of angle between incoming and outgoing quasi-particle. And it shows some oscillatory behavior when the energy of quasi-particle is approaching to close to delta. It's a little bit above delta. So this oscillation may be corresponding, reflecting some information about bound state, but there is no mention in this paper as far as I read. Okay, and then in the B phase, the experimental observation is like this. So this is this line is bulk theoretical value in bulk based on previous Bain's theory. And at the surface, there is some excess scattering. So mobility reduces with respect to this bulk value. But for different depths from 21 nanometer to 58 nanometer, there is no significant dependence or stay constant. So if some surface bound state contribute to scatter electron bubble, and then it is not natural to expect there should be some depth dependence, because the wave function of or probability of finding surface bound state depend on the depth. So number of quasi-particles should be different for each different depths. Okay, but so longitudinal mobility along the A-axis perpendicular to the L vector in the A phase, the experimental value and theoretical value is quite show good agreement. So B phase is somewhat different from A phase. And then this some feature is interpreted by Dr. Tsutsumi, and he calculated this standard theory employing surface bound state quasi-particles, the scattering between surface bound state quasi-particle and electron bubble. And he found the mobility is reduced with respect to bulk value by lowering temperature, because by lowering temperature, the surface bound state occupation is more significant compared to bulk quasi-particle. And and interestingly, depth dependence is cancelled or become flat in this range of depths. So here the coherence length definition is a little bit different from Professor Nagai's definition, but and it is maybe 140 nanometer or something is the coherence length for our case. But in the depth of 400 nanometer, there should be some deviation from this value and approaching to bulk value by further going deeper from the surface. And the important claim by Dr. Tsumi's paper is cross-section. Total cross-section or transport cross-section shows some structure as a function of quasi-particle energy. This quasi-particle is a surface bound state quasi-particle. And this figure is taken at depth equal to Z, coherence length of superfluid. And then it is, so it is rather close to surface, but a little bit distant from surface, 10 times coherence length. This structure becomes sharper. So it indicates the bound state is very much smeared out by hybridization with continuum of surface bound state quasi-particle near to the surface. But go deep inside, it becomes sharper. So I think it is more or less sure about the bubble inside superfluid helium B. There is some bound state is formed. But detail of this bound state is not yet studied theoretically. And maybe we can expect some Majorana nature for this bound state around bubble as well. And surface bound state on the free surface is known to be a Majorana. And looking at the this angular dependence of differential cross section, and then backward scattering is completely forbidden, and it is quite prominent signature of Majorana fermion. Okay, so but for snowball case, the agreement with theory and experiment is not so good as in bubble case. And in particular, B phase case, deviation is quite significant. And there should be something missing in theory. And maybe this some anisotropic structure may be necessary to take into account. And finally, I would like to briefly mention about charged metallic cluster. And preparing this cell, this is target of ablation, and ablating laser is introduced inside liquid helium environment, and then produced clusters are accumulated here by applying electric potential between this plate and upper plate. And video camera is equipped just below this surface, and this is transparent electrode. And tracing the trajectory of particles, one of the example we found showing this kind of thing. So most of particle is just occupying some position like a Wigner solid of electrons, and just vibrate around this lattice position. But some anomalous trajectory shows some traveling go around, or just make a circular motion. And this motion is interpreted by a vortex attachment to this nanoparticle. Either end of the vortex is attached, or a vortex ring is attached to the nanoparticle. So I have no time already, I think. Okay. So to conclude, I talked about short historical review of electron bubbles and snowball in helium-4, and then talked about superfluid helium-3 A phase and observation of anomalous Hall effect. And so this observation is direct evidence of chirality and wire fermions. Wire fermion is a bound state about electron bubble. And in B phase, excess scattering near the free surface is observed compared to bulk mobility. And but this excess scattering show no depth dependence. And so this observation is explained by considering Majorana surface bound state scattered by electron bubbles. And so just maybe this is a kind of joke, I'm afraid, but in future, quasi-particle beam and scattering experiment or angle resolved experiment should be very interesting if it is possible. But such precursor or such idea is already appeared quite a long time ago by Professor Wyatt group in superfluid film 4 to prove Roton beam and Roton scattering and quantum evaporation. And then for helium-3, black body radiator is developed in Lancaster group. And underleft reflection from free surface is observed by this group led by Professor Ishimoto in ISSP University of Tokyo. So thank you for your attention. John?
So thank you, Kimitoshi, for fascinating talk. May I remind the participants in 2021 that they're able to post questions through the Q&A chat box. Maybe I'll kick off by asking a question. I think what's particularly fascinating about the work that you described at the end is essentially the direct observation of currents around the bubble arising from Majorana vial fermions. And not to mention the possibility of identifying the surface bound states on the surface of helium-3b as Majoranas. So that's quite beautiful. One point I would like to ask is for the A phase, the Hall effect measurements didn't go down to the lowest temperatures, whereas of course the theory went to T equals 0. And the Hall effect that's predicted shows structure below your data and also goes to 0 as T goes to 0. So for the general audience, could you possibly comment on the origin of that? And I think we should also switch off our cameras while you're doing that.
Okay. So you are curious about this behavior. And yes. So this quantity alpha is ratio between sigma xy and sigma xx. And sigma xx diverges by going down to low, 0 temperature. So mobility increases infinitely. And so this quantity is unfortunately goes to 0 at absolute 0. But maybe this structure can be accessible by some advanced cryostat.
Yeah.
Is this answer to your question?
Yeah, so you're effectively saying, but these are mid-gap Majorana vial excitations, and so at T equals 0, those excitations are going to disappear, so the currents are going to disappear?
So this is A-phase case.
Yes.
So while fermion formed around bubble should exist, but summary excited quasi-particle die out. Yes. And so no scattering from this electron bubble at 0 temperature.
Okay, thanks. We have another question here from Igor Todoshenko. So maybe if it's okay, initially I'll ask it on his behalf. You showed that there's a decrease in the mobility from what is expected in bulk for the B phase near to the surface. So Igor's asking, could the additional scattering on the surface be explained by Riplonic-like surface waves?
So in helium-4, the mobility due to phonon is so scattering from phonon is quite small compared to quasi-particle in helium-3, and mobility of electron bubble inside helium-4 goes quite high value, and then one can see contribution from lepton. But for helium-3, quasi-particle scattering is quite strong, and we are not yet such range to observe lepton scattering. This is, I think, answer to this question.
Thank you. So I don't know if Igor wants to follow up on that, but thanks for that. Yeah, so we have a question from Waiting Lin Hai, which goes back to the stuff that you were talking about at the beginning, about formation of these objects, extrinsic particles, as it within helium. The question is, I'm curious why the positive ion attracts helium atoms while the electron repels them.
So electron and helium atom have this Pauli repulsion principle, and so it is strongly repulsive. But positive ion doesn't have such repulsion, right?
Yeah.
So this is why electric field from ion attract helium atom, positive ion.
Yeah.
But if ion is some metallic ion, either plus or minus, can attract helium atom because there is not much electron around this positive ion, positive or even negative ion.
Okay, thanks. Earlier in the conference in posters, and I think next week, we're going to hear about the interest in spatially modulated phases in superfluid helium-3 that have been observed, stabilized by confinement. We have a question from Yapa asking, can you speculate on how an electron on the surface of a spatially modulated phase, stripe phase or other pair density wave, would behave? I think there's a question mark about the being able to achieve the conditions to achieve that, but nevertheless, could you address that question?
So yeah, so electrons on helium and the mobility influenced from nature of superfluidity is mobility of Wigner lattice or some surface dimple lattice. And it is really determined by bulk quasi-particle. And yeah, so in this sense, I'm not sure what is influence from forming thin film and put electrons on such thin film. And yeah, it should be very interesting question. And
so maybe clarifying the actual length scale of the Wigner crystal. Typically, in the Wigner crystal, what's the separation of the
it is about 1 micron.
Thank you. Okay, so the next talk is due to start at let me see, 6:30 Indian Standard Time, which is in about 5 minutes. I think let me thank the speaker again. Maybe we should all thank the speaker again for a wonderful talk, and take a short break then before going on to the next presentation. Thank you.
Thank you very much.
Okay, so I believe that we're ready for the next speaker. If he could come to the stage, that would be great.
Hi there.
Okay, so the next speaker is Professor Janendra Jain, who's going to discuss the fractional quantum Hall effect for us. So let me turn over to him to share his screen. And please don't forget to turn your camera off when you're doing the presentation.
Okay, thanks a lot, John. So is my screen visible? Hello? Hello, can somebody tell me whether my screen is visible?
Yes, yes. Can you hear me? Your screen is just fine.
Okay, thank you. So let me begin by thanking Ambrish and the other organizers for giving me an opportunity to provide a review of the status of fractal quantum Hall effect. So this...
I need to interrupt you. Your screen is, for some reason, it was visible, but it's no longer visible.
Just give me a second.
Yeah.
Is it visible now?
No. Yes, now we have it. Yeah, as long as you get a full screen mode. Yeah.
Okay, can you see my screen on full screen mode, please?
Yes, yes, that's
Okay.
just fine now. Yeah.
Thank you. So this figure shows the resistance of two-dimensional electrons as a function of the magnetic field. And I often claim that this is the most beautiful single trace in physics. In fact, not only is the phenomenon beautiful, but so is the underlying physics, which is what I'm going to tell you about. Now, since fractal quantum Hall effect is not within the mainstream of this conference, I'm going to talk a little bit about the history, and I'm going to talk about a lot of stuff that is very well known to the fractal quantum Hall community, but may not be to this community. So let me begin by asking the question, what's the big deal about quantum Hall effect? Well, we have known quantum liquids for more than 100 years now. But the new thing about integer and fractal quantum Hall effects is that they provide a new paradigm for collective quantum behavior. So they do not arise because of pairing or superfluidity or superconductivity, but they are topological states of matter. In fact, in hindsight, we now recognize that the discovery of integer and fractal Hall effects marked the onset of the field of topological states in condensed matter physics. And even today, integer and fractal quantum Hall effects remain the best topological insulators because their existence does not rely on any symmetry for protection. Here I have provided a list of a lot of new concepts, new states, and exotic particles that have come out of the study of integer and fractal quantum Hall effects. So for example, we have fractionally charged particles, particles with fractional statistics, composite fermions. Majoranas were mentioned in the previous talk, but in the modern context, it was in the fractal quantum Hall effect that they first appeared. Then we have non-Fermi liquid metals, one-dimensional chiral Luttinger liquids. We have topological superconductors, and then many of these things which came out of ideas from integer and fractal quantum Hall effects. Then we have concepts like topological order, Chern number, topological quantum field theory and topological quantum computation. So it's a very broad field, but I have selected here a few topics which, from my perspective, are the topics that are most closely related to experiments. So I'm going to begin with a historical background. Then I'm going to talk about composite fermion theory, Fermi of composite fermions, some new developments in fractional statistics, and pairing in fractal quantum Hall effect. So I'm going to give an overview. I'm going to tell you about recent progress, and I'm also going to list some questions which are still unresolved. So all of you know that the quantum Hall effect, or the integer quantum Hall effect, was discovered by Klaus von Klitzing. He found that the Hall resistance has plateaus where its value is extremely precisely quantized at h over an integer times e squared. Concurrent with the plateaus, the longitudinal resistance is exponentially small. It shows an activated behavior as a function of temperature from which a gap can be extracted. Soon after this discovery, Sui, Stormer, and Gossard set out to discover Wigner crystal, but they discovered the fractal quantum Hall effect instead. They observed a plateau where instead of an integer, we have this fraction 1/3. So soon after this discovery, as the sample quality improved, many more fractions were observed. So today we have seen a huge number of fractions. Each minimum here in the longitudinal resistance has a fractionally quantized or quantized plateau associated with it. So let me list some basic facts. So first of all, as you all know, in the presence of a magnetic field, the kinetic energy is quantized into lambda levels as shown in this figure. These are separated by the cyclotron energy. Each lambda level has a finite amount of space for electrons. The degeneracy for each lambda level is given by this expression, B divided by phi naught. This is the degeneracy per unit area. So essentially there is one orbital per flux quantum, where flux quantum is defined here. An important concept will be the filling factor. That's the number of filled lambda levels. That's given by density divided by the degeneracy per unit area. So as we increase the magnetic field, there is more and more room in each lambda level, and therefore we have fewer and fewer filled lambda levels. Another experimental fact is that the plateau characterized by the integer of fraction f is centered at filling factor f. And also for each plateau, each plateau in the Hall resistance, the longitudinal resistance vanishes exponentially with temperature. So each quantum Hall state, be it integer or fractal, is a gapped or incompressible state. Now it's easy to understand the integer quantum Hall effect because that's just a dramatic manifestation of the formation of lambda levels. So when the filling factor is an integer, we have an integer number of lambda levels filled. The state is unique. It has a gap to excitations, and that's what gives rise to integer quantum Hall effect. For fractional quantum Hall effect, on the other hand, we must deal with a fractionally filled lambda level. So at first blush, the fractional quantum Hall problem might seem an impossible problem. And let me explain what I mean. So the original problem has kinetic energy, Zeeman energy, Coulomb interaction, and disorder. Now, we are going to simplify life by considering the limit of extremely strong magnetic fields. In this limit, the first two terms dominate, and therefore we are going to minimize them. We are going to put all electrons into the lowest lambda level. We are going to assume that they are spin polarized in the favorable direction. So these two terms become constant, which we forget about. We are also going to set disorder equal to 0. And then by choosing units appropriately, the Hamiltonian can be written in this rather simple form. Notice that electron mass is not a parameter in the problem anymore. This has no kinetic energy at all. So this is the minimal model for fractional quantum Hall effect. We want to solve this Hamiltonian in the lowest lambda level as a function of the filling factor. And if we could do that, that would display the phenomenon of the fractional quantum Hall effect. Now notice that there is no small parameter in the problem. In fact, the fractional quantum Hall effect is the most strongly correlated system in the world because we measure the strength of correlations as the ratio of the interaction to kinetic energy, and there is no kinetic energy in this problem. To get a feel for what we are dealing with, let's remind ourselves of how we understand superconductivity. So there we first switch off the interaction between electrons and we end up with a non-interacting Fermi state, which is called the normal state. Then we switch on a weak attractive interaction and ask what instability the Fermi undergoes. So that gives an explanation of superconductivity. The fractional quantum Hall effect cannot be understood as an instability of a normal state because there is no normal state for fractional quantum Hall effect. So if we switch off the interaction, we end up with an exponentially large number of degenerate ground states because all configurations of electrons in the available states have the same energy. Just to give you an idea, if I take a system of 100 electrons at filling factor 1/3, that means 100 electrons in 300 orbitals, I end up with this many ground states, or a billion electrons give me this many ground states. So this even 10 to the power 83 is a large number. It's roughly the number of quarks in the entire universe. So a lot of choice produces a lot of frustration. So you would think that electrons would be extremely frustrated. Nonetheless, experiments are telling us that when the repulsive interaction is turned on, a spectacular reorganization occurs to produce the rich phenomenology of the fractional quantum Hall effect. And in particular, at some special filling factors, this humongous degeneracy disappears to produce some unique ground states which are separated from excited states by a gap. So the questions for theory are very straightforward. What is the organizing principle? Since I talked about superconductivity, I could ask the question, what's the mechanism for fractional quantum Hall effect? What are the unique ground states and what are their excitations? And given that there is no small parameter in the problem to guide our thinking, how do we even proceed? Now, this is a problem that could not have been solved without experiments. We have to look to experiments for clues. And that brings me to composite fermion theory. This theory did not come out in vacuum. So there were lots of beautiful works preceding it, which I have listed here, that played a role in the development of the composite fermion theory. From experimental point of view, this observation played an important role. The observation is that the fractional quantum Hall effect is qualitatively indistinguishable from the integer quantum Hall effect. And to drive home that point, I have removed all of the numbers from this plot. And then once I do that, it's impossible to tell which plateaus correspond to fractions and which to integers. So this suggests a deep connection between the fractional and the integer Hall effects and raises the question, can we unify the two? That's precisely what composite fermions do. So in the time that I have, I will not be able to give a detailed motivation for composite fermion theory, but I will still have time to tell you what composite fermions are and what are their essential properties, because this is something that can be done within in a few slides. So a composite fermion is the bound state of an electron and an even number of flux quanta, where flux quantum is again defined here. I have put an asterisk here because this is a model for composite fermions. In reality, the objects that are bound to electrons are not flux quanta, but rather as vortices. But for the purposes of this talk, this is good enough. So this is a composite fermion carrying 2 flux quanta. This is carrying 4. And this 6. So the basic idea of composite fermion theory is as follows. It predicts that electrons in the lowest lambda level capture an even number of flux quanta to turn into emergent particles called composite fermions, which are shown here. The theory further postulates that the interaction between composite fermions themselves is weak and can be neglected for many purposes. The principal property of composite fermions that distinguishes them from electrons is that they experience only the residual magnetic field. So they experience a magnetic field B star, and all of the composite fermion quantities are marked by a star. B star is equal to external magnetic field minus the flux that composite fermions have captured. Okay, so this formula follows from this picture. Composite fermions then form their own lambda-like levels. These are called lambda levels in this effective magnetic field, and we can easily evaluate their filling factor nu star. That's related to the electron filling factor nu by this equation. You may have heard of anions. Anions are often represented by electrons bound to some flux. Composite fermions can be thought to satisfy integral braiding statistics. In fact, the last term here is the statistical contribution. So B star, nu star, lambda levels, they are a direct consequence of the existence of composite fermions and their integral braiding statistics. Furthermore, this physical picture, which is something that's sufficient for understanding many, many experimental phenomena, as I will tell you in a moment, also motivates a single equation that gives wave functions for all eigenstates at arbitrary filling factors. Now, this may seem surprising because there are infinitely many wave functions. How can a single equation give all of them? Well, it does so because it's a mapping. And let me give you the equation. So if we want to construct wave functions at some filling factor nu, we will first determine the effective filling factor of composite fermions nu star through this equation. I will then construct wave functions for non-interacting electrons at nu star and arrange them in increasing order of energy. I will then multiply these wave functions by this Jastrow factor, where Z represents coordinates of an electron as a complex number. So this Jastrow factor precisely attaches 2m quantized vortices to each electron, converting it into a fermion. So this is my wave function, but it has one deficiency. It's not strictly in the lowest lambda level. I'm going to therefore project it by hand into the lowest lambda level and declare that this gives wave functions for strongly correlated electrons at filling factor nu in the same order of increasing energy. So these wave functions cannot be derived, strictly speaking, but they are mathematically rigorously defined. So we can do calculations with these wave functions. And another interesting fact to notice is that for the most interesting cases, which are when filling factor nu star is an integer, there is no adjustable parameter on the right-hand side because the wave function for the ground state or the low energy excited states when nu star is an integer is known without any adjustable parameters. Okay, let me also point out that in addition to constructing wave functions, one can also use a Chern-Simons field theory for composite fermions to calculate various properties. But I won't do anything. In this talk, I will just work with the wave functions, but I just wanted to mention it in any case. Okay, so Horst Stormer and collaborators asked the question, how real are composite fermions? Do they exist? And if they do, in what sense do they behave as particles? Now, let me emphasize composite fermions are extremely complex objects because even a single vortex is a topological bound state in which all electrons participate. So even a single composite fermion, therefore, is a collective topological bound state of all electrons. So how do we know that the picture that I showed earlier has anything to do with reality? Well, experiments are the final judge. And here we are fortunate in two respects. One is that we have mapped the problem into a problem of non-interacting fermions, but a system of non-interacting fermions shows a huge amount of phenomenology. So you can open a book in condensed matter physics, like Ashcroft and Mermin's book, and look at everything that electrons do and predict that composite fermions do the same thing. Furthermore, fractal quantum Hall effect is not a single phenomenon, but it's a collection of a huge body of phenomena. So just to note how rich the field of fractal effect is, close to 100 fractions have been observed to date. And the number of fractal quantum Hall states is actually much larger because at a given fraction, many different types of fractal Hall states can be seen, which can differ, for example, in their spin or Valley polarizations. Fractal quantum Hall effect has been seen in many different systems. So you can take quantum wells with different widths, you can take graphene, you can take zinc oxide, and so on and so forth, and measure lots of properties of all of these states as a function of these various parameters. So there is a huge body of experimental information that's available for fractal Hall effect. In addition, we theorists can do our own experiments and provide even more information. So typical calculations in theory are done by putting electrons on the surface of a sphere exposed to a radial magnetic field produced by a magnetic monopole at the center. So this is a nice boundary condition that theorists like. So we need to know only two numbers for this, number of electrons and the number of flux quanta they're exposed to. Then we can, for not too large systems, we can obtain complete information by doing an exact diagonalization on the computer. So we have all eigenstates, eigenenergies for a lot of systems. So this is a system of 18 particles at filling factor 3 seconds. So for the small systems, we know everything, okay, theoretically. Okay, so let's see how composite fermion theory does. So first, let's begin with explanation of the fractal quantum Hall effect. And this set of animated slides I got from Horst Stormer, and I think it's really beautiful. So I showed this picture on the first slide, and it's been repeated here. So the same panel has been repeated for reasons that will become clear in a moment. So there is integer Hall effect. Then if you go to higher magnetic fields around filling factor 1/2, there are lots of fractions. Then you go further at even higher magnetic fields around filling factor 1/4, there are more fractions. Now, what Horst Stormer did was the simplest thing you could imagine, which is to take the upper panel and plot it as a function of V star as seen by composite fermions carrying 2 flux quanta. So remember, the difference between B and B star is a constant. So all we need to do is move this upper panel leftward by that constant. And once you do that, you notice that there is a quite striking one-to-one correspondence between these fractal states and the integer states. So 1/3, 2/5, 3/7, 4/9, they map into 1, 2, 3, 4, 5, and so on. And the correspondence is so striking that one may feel that one can remove these fractions and replace them with integers. These higher order fractions, they also correspond to the fractal Hall states here, and these fractions can be understood as simpler fractions of composite fermions carrying 2 flux quanta. But you can move this upper panel further left to understand these as integer quantum Hall effect of composite fermions carrying 4 flux quanta. So that's the explanation for fractal quantum Hall effect. It's the integer quantum Hall effect of composite fermions. So this analogy or this comparison establishes the reality of B star, the effective magnetic field, lambda levels, and thus of composite fermions. It correctly predicts these sequences of fractions. It explains all fractions in a unified manner, but it also unifies fractal and the integer Hall effects. Of course, there's nothing special about gallium arsenide. So this is a fractal Hall effect in monolayer graphene, and the fractions that are seen precisely follow these sequences that are predicted by the composite fermion theory. This paper was actually about fractal Hall effect in double layer graphene, and those fractions, so there's a huge number of fractions observed here. They can be also understood in terms of a generalization of composite fermion theory to double layer systems. Okay, how about quantitative validity of composite fermion theory? So let's compare theory to computer experiments. So I'm going to show you in the next couple of slides or next few slides results from 2 completely independent calculations. One is brute force exact diagonalization on the computer, and the second is the composite fermion theory. So neither of these calculations involves any adjustable parameters, and therefore the comparisons I'm going to show you represent an unbiased test of the composite fermion theory. Okay, so I showed this earlier. These systems are fairly large. They are 14, 16, and 18 particles at filling factors 1/3, 2/5, 3/7. If you look, so the quantum number, the appropriate quantum number here is the total orbital angular momentum because of the geometry that we have used, the spherical geometry. At each quantum number, the number of states that would be degenerate in the absence of interaction is from a few 100,000 to a few million. So these systems are quite non-trivial. All of the structure that you see here is because of Coulomb interaction. If we switch off the Coulomb interaction, all of these states would collapse into one energy. And you can see that gaps open up. So that tells us that there is some non-perturbative physics in play. Okay, so what does composite fermion theory tell us? So according to the picture that I gave you, composite fermion theory would say that this is 1-filled lambda level of composite fermion. This is 2-filled lambda levels. This is 3-filled lambda levels as shown here. And we know precisely the wave functions associated with these pictures. So the first thing we can do is just forget about quantitative comparison, just calculate the quantum numbers, the angular momenta. So ground state has angular momentum 0, so it's spherically symmetric. These low energy excited states are interpreted in terms of a particle-hole pair of composite fermions, and again, this picture produces the right quantum numbers for these states. We then go further and calculate the expectation value of the Coulomb interaction for these wave functions, and we get the dots here. So again, let me note that there is no adjustable parameters in either calculation. And there is, you can see a spectacularly good agreement between composite fermion theory and exact diagonalization studies. We can go away from the special filling factors. So these are somewhere between 1/3 and 2/5. These are the exact spectra, and this is what composite fermion theory gives. We can actually understand higher and higher excited states by exciting composite fermions across higher and higher lambda levels. So, for example, this band consists of either 2 composite fermions excited by 1 lambda level or 1 composite fermion excited by 2 lambda levels. Again, the dots provide a very good representation of the dashes, which are the exact energies. Okay, so this is the background. Let's now come to the 1/2 state. That's the second thing on my list. So there is a puzzle at filling factor 1/2. In fact, at some level, nothing is seen at 1/2. Okay, there is no quantum Hall effect, and the resistance, longitudinal resistance, does not show anything particular. But the puzzle is, why is there no fractional Hall effect at filling factor 1/2? 1/2 is the simplest fraction. Why don't we have fractional Hall effect here? Well, you will notice here that 1/2 maps into zero magnetic field. So another way to say that is that at filling factor 1/2, when electrons capture flux quanta to turn into composite fermions, they absorb all of the magnetic field. And therefore, the effective magnetic field for composite fermions vanishes. It's zero. So composite fermions are predicted to form a Fermi sea here. Fermi sea has no gap, and that explains the absence of fractional quantum Hall effect at filling factor 1/2. Now, let me note how remarkable, how dramatic this prediction is, because there was no kinetic energy in the original problem, in the defining problem. So here, a Fermi sea is arising completely, entirely from interaction. The Fermi sea of composite fermions has been fully confirmed by experiments. And in fact, it allows for a direct measurement of the effective magnetic field B star. So let me show you some experimental results here, including some very recent results. So the idea is to move slightly away from filling factor 1/2, where composite fermions see a tiny magnetic field B star, and they execute a large cyclotron orbit. If one could measure the radius of the cyclotron orbit, that should be given by this formula, where the Fermi wave vector for composite fermions is square root of 4 pi rho. So many experiments have measured the radius of the cyclotron orbit. Perhaps the simplest one to understand is to imagine throwing current into a constriction here and catching the current into another constriction. And from that, one can measure the deflection of the particles which are carrying current. And all of these experiments are consistent with effective magnetic field B star. In recent years, people have taken a closer look at the composite fermion Fermi sea, and that is justified because this is, from the vantage point of electrons, a strongly correlated system. It's actually an example of a non-Fermi liquid. So there are two aspects which have received attention recently. One is called the Luttinger theorem. As you know, a fundamental tenet, a fundamental prediction of the Landau Fermi liquid theory is the Luttinger theorem, which asserts that when the interaction is turned on, it does not alter the volume of the Fermi sea so long as there is no phase transition. In other words, the Fermi wave vector remains invariant. So that's the case for ordinary fermions, but I should have been 1/2 here. At half filling, there was no Fermi sea to begin with. So how accurately does the composite fermion Fermi sea satisfy the Luttinger area rule? That's one question. The other question has to do with particle-hole symmetry. So if we restrict the Hilbert space to the lowest lambda level, there is an exact particle-hole symmetry for electrons. So this means that we can define the problem either in terms of electrons in the lowest lambda level or in terms of holes. So at half filling, these two descriptions are equivalent. So half filled glass is equal to half empty glass. The question is the formation of composite fermions consistent with the particle-hole symmetry for electrons? Now, one can treat this problem at various levels. One is to construct explicit wave function, which I have shown here. So this is the wave function for the Fermi sea of electrons. This Jastrow factor converts electrons into composite fermions, which then we project into the lowest lambda level. So if you look at this wave function, there is no reason to think that it satisfies particle hole symmetry. It's certainly not imposed on this wave function. But nonetheless, one can construct this wave function on the computer, and one finds that it does satisfy particle symmetry to an extremely high degree. So it has an overlap of 99.9% with its whole conjugate.
Right now, we can't see any wave functions, by the way.
You can't see the wave function?
No.
That's very strange. Okay, can you see the bullets? The bullet points, can you see the text? Okay, can you hear me?
Last bit we can see is about the Luttinger theorem.
Sorry, there seems to be some sort of disruption. Maybe it's at my end. Can you hear me?
Yeah, we can hear you.
Okay. Do you see the slide?
Now we can see the slide, yeah.
Okay, thank you. Yeah, sorry about that. The recent experiments have measured the Fermi wave vector of composite fermions very accurately. The idea is to do transport in a system where which is exposed to periodic modulation of density, a very slight modulation of density, but periodic with a period A. Theory predicts that the resistance would show minima when the diameter of the cyclotron orbit is given by this formula, where I is an integer. So converting this into magnetic field, theory predicts that minima would be seen in the resistance at these values. So these values are marked by these vertical solid lines, and they do agree with the positions where minima are seen experimentally. So, at first sight, you're very happy, but then the experimentalists notice that the agreement is better on the right-hand side compared to the left-hand side. And then they realize that they can get a much better agreement if they if they define the Fermi vector in terms of density of the minority carriers. So if the number of electrons is less than the number of holes, we use the electron density here. If the number of electrons is higher than the number of holes in the lowest lambda level, we use the hole density here. And that gives these dashed vertical lines, which agree very well with experiments. Okay, they have also carried out precise experimental tests of the Luttinger theorem. So here are the experimental positions for the primary minimum on either side of filling factor 1/2. The red curves show the predicted positions using this formula, and you can see that there is an extremely good agreement between the predicted position and the observed position. So the conclusion of this experiment was that the composite fermion Fermi series satisfies Luttinger area rule extremely accurately. The experiments also satisfy particle hole symmetry to a good approximation. So somebody has their microphone on, creating some noise in the background. The particle hole symmetry here has to do with reflection symmetry along this axis. And so this was a bit of a surprise. In this experiment, this kappa is the lambda level mixing parameter. It's the ratio of this Coulomb energy to the cyclotron energy, and particle hole symmetry is satisfied even when kappa is not particularly small. The green dashed curve is a prediction from Sohn or Halperin-Reed theories that are about those on the previous slide, which got skipped because of the glitch with the internet. But So there is a reasonable good agreement, but nonetheless, there is a significant deviation between experiment and these theories. Okay, let me come to the next topic, which is fractional statistics. So you all, I'm sure, know about anyons, which were predicted by Lynch and Murheim and by Wilczek. They realized that in 2 dimensions, quantum mechanics allows for the possibility of particles which are neither fermions nor bosons, but whose exchange produces a phase factor rather than a sign. Another way to think about anyons is to imagine a particle looping around another particle. And for anyons, this produces a phase because this loop corresponds to 2 exchanges. Anyons were thought about, or they were conceived prior to the discovery of fractal quantum Hall effect. And at that time, they were perhaps just a theoretical curiosity, but it was predicted by Halperin and by Arova, Stephen, and Wilczek that the quasi-particles of the fractal Hall effect obey fractional statistics. So this, one can now imagine measuring the fractal statistics by in a geometry like this one. And a quasi-particle that's moving along the edge of the fractal Hall system can take 2 paths. It can either just go from here to here, or it can go around this, this area and then come back here. The interference from these 2 paths gives us the phase associated with this closed loop. And the change in the phase when we insert another quasi-particle in the interior should give us the fractal statistics. Okay, so this seems like a natural way to measure fractal statistics. But there are 2 experimental challenges. One is that the phase associated with this loop also contains an Arnold-Bohm phase because these are charged quasi-particles. So the fractional statistics contribution is like a small correction to the Bohm phase. The other problem was that if the area of this path, area subtended by this path is very small, then the results are dominated by Coulomb blockade effects. If the area is too large, then the phase information is lost before the quasi-particle completes its loop. So recently, the Purdue group, headed by Mike Manfra, and they were able to eliminate or suppress Coulomb blockade effects by epitaxially growing screening layers very close to the layer containing this sample. And indeed, they detected phase slips of magnitude 2 pi over 3 at filling factor 1/3, which are consistent with the theoretical expectation. So this has created a lot of excitement because this is the first reliable, or I should say one of the 2 very compelling confirmations of the idea of fractal statistics. The other experiment, which I have not talked about, it studies current correlations resulting from collisions between quasi-particles. So these current correlations have information about fractal statistics, and they have also found that at filling factor 1/3, their results are consistent with this value for the fractal statistics. Okay, I come to the last topic, which is the state. Now, I just told you that at filling factor 1/2, we have a Fermi sea of composite fermions. So at filling factor 5/2, which is half-filled second lambda level. So 2 here refers to filling factor of the lowest lambda level when both up and down spin levels are full. So at 5/2, we have half-filled second lambda level. One would naively expect a Fermi sea of composite fermions, but experiments show a fractal Hall state instead. So what's happening? So this has given rise to a beautiful picture, which is built upon a series of remarkable emergences. And if it all works out, it would lead to topological quantum computation. So what are these emergencies? First, composite fermions are formed at half-filled lambda level. But rather than form, and they try to form a Fermi C, but the Fermi C is unstable to pairing. Composite fermions instead form a px minus IPY superconductor. The wave function of this state is shown here. So proceeding in the standard manner, if I assume that the wave function of a pair is 1 over zi minus zj, take product over all pair wave functions and anti-symmetrize it. So this is the BCS wave function written in a particular form. I then multiply by this Jastrow factor, which converts electrons into composite fermions to give me a paired state for composite fermions. Now this factor is precisely what is called the Pfaffian, and therefore this wave function is known as the Pfaffian wave function by Moore and Reed. So pairing opens a gap, and therefore it produces fractal Hall effect at filling factor 5 halves. Now, before I move further, you might ask, how can pairing arise in a model with purely repulsive interaction? Remember, we only have Coulomb interaction between electrons. The reason it can happen is because the objects that are pairing are not electrons, but composite fermions. The interaction between composite fermions is different from the interaction between electrons. It has to be calculated, and there is no reason why it can't be slightly attractive. In fact, calculations show that the interaction between composite fermions is repulsive at filling factor 1/2, but attractive at filling factor 5 halves. Now, this is a topological superconductor, so the Abrikoso vortex of this state supports a zero energy bound state, which is essentially an equal superposition of the composite fermion creation and annihilation operators. This is a Majorana particle. It obeys non-abelian braid statistics. And in principle, one can imagine constructing qubits using this Majorana particle. For example, if the 1 and 2 can be put in on and off position, and one can toggle them, toggle between them by passing another Majorana through the path connecting these two. Okay, so there is a lot of vigorous work going on to confirm the validity of these steps. So not all of these steps are fully confirmed. In particular, I would like to mention recent experiments from Moti Heibloom's group, where they measure thermal Hall conductors. So let me describe the experiments to you. The thermal Hall conductance for a two-terminal measurement is defined as djq dt, where jq is the heat current. For a single channel or a single lambda level, theory predicts that thermal Hall conductance is given by this expression, which I will call kappa naught. Indeed, when the filling factor is an integer, measure an integer value for thermal conductance, thermal Hall conductance. When the filling factor is given by P over 2P plus 1, experiments also find that the thermal Hall conductance is equal to P. That's understood in terms of composite fermions because this filling factor maps into filling factor P of composite fermions. So we have P lambda levels of composite fermions. Now, for 5 halves, it's predicted that there is also a Majorana edge mode, and that is predicted to contribute a half integer to thermal Hall conductance. So these experimentalists measured the thermal Hall conductance at 5 halves, and they find that it's given by 5 halves. So that was nice because it's indeed half integer thermal Hall conductance, but it turns out its value is not consistent with what is predicted for the Pfaffian state, which is 7 halves, or it's not consistent with also what is predicted by the anti-Pfaffian state, which is the whole partner of the Pfaffian state, which is 3 halves. So this has created a lot of excitement. This experimental result is not fully understood. One can try to understand it either disorder or in terms of lack of equilibration of the branch, but there are more recent experiments which really convincingly point to a particle-hole symmetric pairing of composite fermions. But it's not known what that state